Thank you again for everyone for coming out to St. John's Center for the Arts. Today we have a great lecture on the go by Dr. Donald L. Forbes, titled Rising Sea Levels in the Landscape of Alma Dam. So at the risk of spoiling too much, I do want to thank you in advance for what you're about to teach us. Thank you for coming down to Aarschot. And I'll turn it over to you. At the end, if you do have questions, we will have a microphone. You can see me and you'll be able to ask your questions. Thanks.
Thanks, Jason. Uh, it's always a pleasure to come to Arashat. I first came here a few years ago at the instigation of Dan Lane, who unfortunately isn't in town these days. They've gone to visit grandchildren in Ontario. But it was Dan who uh, proposed Ilma Dam as one of 6 communities in a project called Sea Change, which was looking at climate change adaptation and rising sea levels in coastal communities in Canada and the Caribbean. So we had 3 communities in Canada. Ilma Dam was one of them. The other 2 were Iqaluit and BC. I'm sorry, I'm blanking. And then we had 3 in the Caribbean: one in Guyana, one in Trinidad, and one in Bequia in the Grenadines. So my involvement I was just about at the point of retirement, and my involvement in the Ilma Dam work was not extensive. But I think we know enough to be able to say something useful, and I hope that you'll find that interesting. I'm intrigued to be speaking to you in this lovely sanctuary on a Sunday afternoon because both of my grandfathers were preachers. And Sunday was a working day, and quite often they would have 3 services in the day, so there would be an afternoon service. But I don't intend to preach to you this afternoon. There might be a few exhortations about adaptation. Uh, and some of my other affiliations are there. I'm retired from the Geological Survey of Canada at the Bedford Institute of Oceanography. That was my main day job. And then I had students at Dalhousie and Memorial. Uh, so that's the background. Anyone recognize this place? Yes, you know, if you take the road to Janvin Island, you will come to that corner. So here's a calm morning in Petit de Gras, and sometimes the coast can be very beguiling, and you can be convinced that it's a peaceful place, but it's not always so. And it's during these kinds of events that we see most of the coastal change. And the concern, of course, now is with rising sea levels, with a warming climate, more energetic storms, that we will see more damaging events during storms. So just briefly, what are some of the drivers of coastal change and sea level, particularly on a long-term scale? Sea level is, you know, a first-order driver. If the sea level drops 50 meters, then the geography changes. And if it comes up by half a meter or so, we may think that that's not too serious unless we have a wharf or something at pretty much at sea level now. But there are other implications as well. I'll come to some of those. So rising sea level, but also extreme water levels. These are things like storm surge, storm setup, run up. So that as you can see with these waves, they're washing over the breakwater. This is actually at McNabbs Island in the mouth of Halifax Harbor. They're washing over the breakwater, they're breaking high over the breakwater. So if you have infrastructure, you know, well above the highest still water level, you still see damage. And we know that sea level's rising in the Maritimes from a number of indicators. We see lots of geological indicators of that. We have tide gauge records I'll come back to. One of my favorites is this mooring ring that was in the seawall at Louisbourg, which was put in 1743. And the blue there shows the blue shading shows the high tide limit in 1998. So you can see that no one would put a mooring ring at that elevation if the tide came that much higher. And then there are many places around Nova Scotia and PEI where we see rooted stumps in the shoreline. It's evident that the forest used to extend further seaward, and now the waters come in. So there are other things that drive coastal change, and these include groundwater, seepage, and in some places freeze thaw. So if you have a clay cliff and you get a lot of freeze thaw, that can actually be a cause of erosion. On the north shore of the St. Lawrence estuary, they find that that's a really significant driver. And then the soil, the cliff stability is a function of slope stability. So there are all kinds of geotechnical components that influence whether or not you'll have failure, which will bring sediment down into the wave zone where it can be washed away. And to keep the cliff eroding, you actually have to have the energy to move that sediment away. And then all kinds of things related to fluid dynamics. So wind and waves, and wave transformation as it comes into the shoreline. So it shoals, it steepens, and then eventually will break, and you could have run up that will wash over the beach. Tidal inlet processes that can influence the beach some distance away from the inlet. And I mentioned tsunami there. I actually would be very intrigued if people have stories of the 1929 tsunami in Île-Madame. But it was a damaging event, particularly in Newfoundland. And although it's rare, there is a finite probability, a very, very small finite probability. Your chances of being hit by lightning are probably much higher. But nevertheless, we need to be aware of that. And then I imagine here, but perhaps less so these days, ice, so certainly in the Gulf of St. Lawrence, the nearshore ice, where ice actually comes on shore and into buildings, so they're built too close. And then offshore ice, which I should say nearshore and offshore, offshore ice, which can dampen wave activity. So it used to be in the Gulf of St. Lawrence that we had enough ice that many winter storms would not generate waves. And over the years, and I think we're beginning to see the implications now, as there's less and less winter ice in the Gulf. We have more of those. We may not have an increase in storms, but the number of storms that come with open water leads to an increase in erosion. So these drivers, they interact with the landscape, the geology, with the sediments, the landforms, the marshes, and even the infrastructure that we build, and they erode and they move and they deposit sediment in other places, and that causes a morphological change. This was actually taken during Hurricane Hortense back in the mid-90s, showing a beach that was being overtopped, and this beach actually never recovered. So actually, not only do coastlines change, but oceans change. We tend to think of the Atlantic Ocean as something that's been there forever. It's been there for about 170 million years. And prior to that, for example, 600 million years ago, Laurentia and Gondwana divided, and the Iapetus Ocean opened. And it opened by a process of seafloor spreading from a central rift. So if you remember the eruption that occurred near Reykjavik in Iceland earlier in the year, that was on the mid-Atlantic rift, and that was part of that process of the Atlantic getting wider and wider. And so we had the Iapetus Ocean. There were others as well. And then after a while, the continents would drift together again. And as they do that, one slides under the burst, if you like, of these ice ages occurred about 100,000 years apart. So the last one was about 23,000 years ago was the peak. And we had ice that covered Isle Madame. In fact, it went virtually to the shelf edge of Canada. And you can see I've marked where Isle Madame is in that figure. So all of these processes interacting gave us Isle Madame as it is today. This is actually a diagram by Eric Force, who used to live here. He was a professor at the University of Arizona, I think, working with Sandra Barr from Acadia. And it's, I think, the most up-to-date map of the geology of Isle Madame. And you can see, first of all, that there's a sort of west-southwest to east-northeast orientation of the rocks. And so some of the topography is a function of that orientation. The other thing that's fairly obvious, I think, is that all of those solid lines and even the heavy dashed lines are faults. So cracks in the rock where rocks shifted. And you can see that, for example, the alignment of this side of Arichat Harbor, the alignment of the north side of Arichat Harbor, Petit Gras Harbor, the alignment of the shoreline that extends from Pondville up toward Cap La Ronde. Those are all function of the orientation and location of those faults. But then the glaciation put an imprint on top of that. There were actually, in the last 75,000 years, there was ice that moved in virtually every direction over Isle Madame. But the most prominent ones were one that was to the east, the faint green arrows that you can see there. And the landforms actually demonstrate this. And one that was to the southeast. And that one to the southeast is particularly because it imprinted over the earlier one. So it's indicated by all of these drumlins, which are egg-shaped hills that are streamlined in the direction of ice movement. And ice that's moving rapidly forms these features. So they actually demonstrate where there was fast ice flow and ice, we talk about a nice stream. And there's some beautiful examples of that in Isle Madame. So here in this lovely archipelago that we have over toward Jandron, you can see each of those dots and lines is the axis of a drumlin. And each of those drumlins, when the coast intersects it, it will begin to form a cliff, and that can then be a locus for sediment production that forms beaches to each side. And there's only so much sediment in the drumlin, so after a while it gets exhausted, like Cap La Ronde is exhausted, and there's no more sediment coming into the system, and then this whole system can step back. So it's actually a beautiful example on an island that Google told me was Green Island, but it's not. I'm not sure what its name is, but just near Jandron. Very much like this. This is at the mouth of Chesapeake Inlet outside Halifax, but it illustrates the point. This Storyhead drumlin is sort of in old age. It has just a little bit of sediment left. It's formed these beaches that trail out on each side. One is was connected, but isn't any longer. It's the one I showed you, the waves overwashing. And then the other one is a spit, but you can see it's broken up because it's getting less and less sediment. And so the same sort of thing up at Cap La Ronde. You can see here are the axes of the drumlins, and they act as anchor points, and they act as sites of sediment production. And then after a while, they get exhausted and overtopped. I mean, you're left with a landscape that is just the sort of the boulder shoal, or maybe some bedrock, where the base of the drumlin used to be, and it gets submerged. So then I showed you 23,000 years ago. Eventually, we came to the end of the Ice Age. the continental ice sheets of North America began to, and Europe began to wane. Um, and there was also a balance of sea level, which I'll come back to in a second, but it means that there was more exposed land on the outer banks. And actually on the Grand Bank out here, there was a large landmass, about the size of Nova Scotia. And it's interesting that today capelin, which spawn only on gravel beaches, spawn out on the outer bank because they started spawning on beaches on that landmass. And eventually the landmass went away, but they continued to spawn there. So when you, to build an ice sheet, you have to move water out of the oceans onto the land. And so the weight over that area of the land increases, and the crust is depressed by that weight. Actually around the outsides of that depression, it's pushed up. If you think of, well, we used to use the analogy of a waterbed, but I don't think anybody has waterbeds anymore. But a beach ball, if you push a beach ball in, there is a little rim around the outside of where you push. And that's called a marginal forebulge. And we live in the area of a marginal forebulge. So when the North American ice sheet was at its peak, there was significant depression in the middle of the continent. But in our area, we were actually pushed up a little bit, which is partly why that land was present on the Outer Banks. And the other thing is that as you move water out of the oceans, the volume of the oceans goes down, so sea level goes down. And when you melt ice sheets, it comes back up. And even projections of the future, we need to be figuring out how much water is coming out of the various ice sheets that exist today. So as a result of that, this may be a little tricky to understand, but this diagram shows time in thousands of years. So back in time with 15,000 years. And this is elevation with current sea level being here. And the sea level in our area was depressed. And then it's been rising since this low stand that was about minus 55 meters, something like 11 and a half years ago. The red there, this is a model that calculates these levels at a series of nodes. And so the nearest ones are Canso and Forshu, which is this red line and this purple line, I think. They bought it, actually, no, this brown line. So sea level was, the relative sea level relative to the land surface was 55 meters lower. All around Isle Madame, it was not an island. PEI was not an island 11,000 years ago. You could walk to the island, and in fact, we think indigenous people did. And you can see those large land masses on the outer shelf are getting smaller, but still quite substantial. And 9,000 years ago, you could still walk to PEI, but there's much less on the outer banks, and that's because that forebulge is collapsing and migrating toward the northwest. And finally, about 65,000 years ago, the water came in around PEI, it became an island once again. You can see we have just an enlarged Sable Island on the outer shelf. And although global sea level hasn't changed much since 6,000 years ago, our land surface has continued to subside. So we have had rising sea level for 11,000 years in Isle Madame. It's nothing new, but if it starts to come up more rapidly, then that makes it more challenging. So we had, for example, we had this progressive, as I said, it wasn't an island. We had this progressive flooding of Isle Madame, and water came in around all of these drumlins. Here is the green island I mentioned. That's apparently not its correct name. And I see I spelled Creighton Island wrong, but At any rate, you have this progressive flooding of the drumlin field with the rising sea level and all the other parts of the island. Um, and so each of these drumlin headlands becomes a locus of sediment supply. It forms these beaches that link up to Laurier Island. Green Island, quote unquote, probably had a beach across here and a beach across here. But they stretch, and as they stretch, they need more sediment to maintain their continuity, and eventually they breach, and you end up with spits. I'm going to try to play. So when we go down on the bottom and look at some of these old coastal deposits, this is looking at an old salt marsh estuarine deposit of PEI. It's just where I have this video, but I thought it would be a little bit of light relief. So this is about 20 meters depth, and is about 3 kilometers offshore, 6,000 years old. It gives us an indication of how much the coast has come back in that time. But it also shows us kind of the product when the coastal ecosystems get inundated and flooded, and reminds us that we need to be thinking about how do we maintain our current coastal ecosystems that provide a lot of ecosystem services in a rising sea level. Let's run that one more time. So the cliff you can see in the background is about 1.5 meters high, and it's formed by waves that quarried out the soft mud when it's exposed on the seabed. So, we need to think about maintaining salt marsh and other coastal systems with rising sea level. The way we do that is by allowing them to migrate upslope. And so if we have roads or other infrastructure that blocks their migration, we can end up losing them as the sea comes in, and the outer limit of the marsh migrates and the inner limit can't. It's actually called coastal squeeze, and that's one of the things that's recognized as a challenge with rising sea level. So now I'm going to change topic here a little bit and talk about climate change. And this, to me, is a profoundly moving figure that came out of the last report of the Intergovernmental Panel on Climate Change, the IPCC. It's showing on a time across the bottom, it's showing from 1900 to 2100, how red the color is an indication of how warm it is. I'm this fellow with the cane. I don't have a cane yet, but I'm getting close to it. I am actually past 70. So this is me, and I'm not going to have to face much, no matter what emission scenario we face, how we react to the threat of climate change. But my children are in this generation, and my granddaughter, who was born this year, is in this generation. So when she's 70, how do we maintain an environment that is habitable, really? And we talk about the impacts of climate change today in terms of more forest fires and more intense storms and so on. We've barely seen what's coming. We've barely seen what's coming. So these are projections from the IPCC. Actually, the last report hasn't changed much in terms of future temperature. And these emission scenarios that are used are, well, if we are very effective in mitigating our emissions, and we have a major transition of our economy that leads to less greenhouse gas, then we might be able to keep that purple line where we actually peak and bring it down. the way we're going right now, we're much likely to be following that upper line. And ideally, we would at least find something in the middle. So that, by the time you get to 4 degrees, things will be very unpleasant. In terms of sea level, what does it mean? Well, again, the sea level projections are based on these scenarios. There's actually an extra wrinkle now that involves some of the socioeconomic components that lead to those scenarios. And then they have a whole series of global models that are run for any given scenario. And the median, the value that where 50% of the model results are higher and 50 are lower, it's called the median value. And that's what those solid lines are. And then the shading around those is the statistical uncertainty. And so we're looking at, and this goes up to 2150 because things aren't going to stop in 2100. For many years we've been talking about what do we face by 2100, but in fact we're now looking to 2300 with the models because it's clear that 2100 is just the beginning. And none of these actually peak. They're all climbing a little bit. The other thing about where we live, this is complicated, is basically they're all they're maps of the world for various scenarios. And the one thing I want you to notice is that in Northeast North America, we have higher values than almost anywhere else. So we are going to see an amplification of sea level rise over and above those global projections. Unfortunately, the Point Tupper tide gauge only ran for a few years and was terminated in 1991, so we can't do this kind of analysis for locally. But for Halifax, which is not too different really, if I showed you that diagram with the sea levels that bottomed out and came up, Halifax the line for Halifax was very close. So this is the tide gauge record for Halifax from 1895 through to 2020. And overall, well, first of all, you can see that it was not rising very much until about 1920. That was probably a little lower than the long-term 19th century average, but it was rising very slowly, and then you can see it changed. And the second thing you could see is that there's variability. So 30 years is taken as a climate, if you're defining climate, is based on 30 years of records. So taking this 30 years at a time, we actually see that from 1920 to about 1950, we had quite a rapid rise in sea level. Then it began to sort of ease off, 2.3, these are in millimeters per year, which translates to 23 centimeters per century. And we were beginning to wonder in the 1980s if maybe we weren't going to be dealing with rising sea level so severely. And then you can see since 1990, for almost 50 centimeters a century. And the expectation from all of the models is that is continuing to increase. In terms of what the projections are for Ile Madame, this is some work that was done. I was involved in some of the early work on this, and colleagues on the West Coast have been leading this. So we now have projections for various scenarios for any place in Canada, around the coast of Canada. And so we can actually generate these projections for Ile Madame. But so much depends on which scenario we can expect and what statistics we take. So the one on the left is for a much more modest emission scenario where we may not be facing such an increase in temperature. But if we look at the 95th percentile, the range, within the probability, we get 80 to 100 centimeters of sea level rise. The other is for a higher emission scenario, but the median. So it's a bit complicated. Your values depend on what scenario we end up tracking. And at this point, we don't know what that scenario is going to be. So there's a tendency to say, well, we should take this upper level scenario because it could happen and be prepared for that. The other thing I mentioned that sea level is one thing to see the rise in sea level, but it's another to see the effect of that on the frequency of high waters. So this figure is a little complicated. It's what's called a return values, an extreme values probability distribution. So across the bottom are return period in years. So this is a 1 in 50-year storm. This is a 1 in 10-year storm. This is a 1 in 100-year storm. And then the elevation, the water level elevation. And these are the highest, this is the distribution of annual maximum water levels in Halifax Harbor. Here's Hurricane Juan, which was the highest we've ever had. Prior to that, the record was a winter storm in 1967. So we look at all of these, and they tell us, what elevation, what flood level we can expect for a 1 in 50, 1 in 100-year storm. If we increase the sea level, we bring that whole curve up. And the effect of bringing that curve up is that a 1 in 50-year storm becomes a 1 in 2-year storm. That's the impact of sea level rise. It's really on that storm distribution and extreme water levels more than the average sea level. And I've not heard a lot about the impact of Fiona and Neil Madame, but I imagine it was phenomenal. I would love to hear from you about that. So this is an image of the storm just offshore. The other, which comes from Ryan Snodden at the CBC, is showing the number of hours with gusts over 100 kilometers per hour from that storm. And you could see how really extensive it was. Because although it was a Category 3 hurricane just offshore that transitioned to what they call a post-tropical storm, that actually allowed it to expand. And we lost trees in Maitland, where it's just a good distance away from the center, where I didn't expect we would have that impact. Our yard was filled with trees. And you were right in the track. You were right in the track of that storm. And one of the effects of climate change has been that we are more frequently seeing warm water over the shelf. The Scotian shelf is increasingly warm enough to sustain hurricane energy even after the storm comes into our waters. So in the old days, tropical storms would come up. Usually they get dampened down when they got out of the Gulf Stream and onto the Scotian shelf. And that's not happening so much. So Juan actually increased as it came toward Halifax. And I don't know specifically about Fiona, but this is a diagram that's actually making the point that the water was warm enough to sustain the energy. So what can we expect in the future? There's a lot of uncertainty about storm projections. There's still a lot that isn't fully understood. So the latest IPCC report says that the models are consistently projecting increases in the proportion of intense tropical cyclones or hurricanes. That's to say Category 4 and 5. And actually there's talk now about how perhaps there should be a Category 6. And one of the things about that most recent storm that hit, the second one that hit Florida, was it intensified from 1 to 5, I think in something like 24 hours. So that speed of intensification is also new. And then so as the coastal effects depend on the intensity, the size, the track, projected increases in sea level, average tropical cyclone intensity, and tropical cyclone rainfall rates each generally act to further elevate future storm surge and freshwater flooding. So we're expecting more. The statistics are still not really well defined. So that's climate change and sea level rise. What does it mean in Ile Madame? The province, as you know, backed off on implementing the Coastal Protection Act. And they rushed into service an app, which is quite useful, but really doesn't tell us everything we need to know. So this is Nova Scotia's coastal hazard mapping tool. I encourage you to look at it. It's very um, instructive. And it's lovely in the sense that it makes use of the LiDAR digital elevation models that have been developed. When we were doing the sea change work in Île Madame, one of the things we were advocating was, please get LiDAR coverage of all of Nova Scotia as soon as possible, because it has so many uses, and one of them is particularly in dealing with projecting flood levels. And so this actually has happened. And we have wonderful data. It's all available online freely at GeoNova. And they make use of it in this tool. They also have a version where you can see the orthophoto images. So this is Arashat Harbor. Superimposed, you may be able to see the faint white lines there. Those are property boundaries. And the blue line is a quote unquote worst case scenarios flood level in 2100. The various issues with it, but it's nonetheless useful. That's effectively a 3-meter contour around the coast of Île Madame. And it will tell you whether you're low or high. Problem is, so then you can say we go to La Vieille Forge, and we click on that property, it will bring up this projected worst case flooding scenario here. And it has 3 components. It has a projection of the highest spring tide, and this is relative, they say relative to mean sea level. I think they mean the new geodetic vertical datum CGVD 2013, which is the new standard, which is much closer to sea level than the previous datum. So 60 centimeters above mean water level. They have a storm surge of 1 meter, which is supposed to be a 1 in 100 year storm. And remember what I told you about how the 1 in 100 can become the 1 in 2, which means the new 1 in 100 will be much higher. I'm not sure how they've come up with this 1 meter. And then a sea level rise of 1.4 meters, which is that upper limit of the highest scenario. So that one's being very conservative. The storm surge height, I'm not sure. But it is a reasonable estimation of where if you build above that level, you're probably safe from being flooded at still water. But remember, I talked about run up, set up. You need to be above still water to be safe. Anyway, and these values don't change all around Île Madame. So they change around the province, but for Île Madame, it's 3 meters, the sum of these components. 3 meters is what they've used all around Île Madame. So here's Pondville Beach. One of the things is it only comes 100 meters back from the high water line, so we know that all of this beach would be flooded in a storm that came this high. But the app doesn't show that. Here is Petit de Gras. We can see, for example, where's the? I think this is the fish plant that was flooded in a storm that happened shortly before we began the sea change work. This is Discus, and that's available. You can go online at. I'll put it back. I'll put the app. The link is in one of the slides. I'll put it up afterward. But you can go all around Île Madame and find whether your property is affected by that line. So it tells you what is likely to be flooded, but it may miss some. My impression is it's missing some, and it also is not going to tell you about erosion. So it's just telling you about still water level. And then whether you'll have higher impacts depends to some extent on your exposure. So if you're in Lennox Passage and your fetch is very limited, you may not see much wave enhancement, but on the outer coast, obviously you do. So this is where we started out at the beginning of the talk. The photo was taken looking along this shore here. And the app is telling us, for one thing, that the roads are going to be flooded. So if you want to get to this property, it's not just getting across the beach to the property, but it's getting across this bridge and this link and so on. In fact, one of the things we did with Sea Change was to map out where the road was low, and highways might want to think about raising the elevation. The other thing, as I said, it doesn't tell you about erosion. So these are two properties that have buildings on them out there. One is for sale. At least there's a for sale by owner sign, and I'm not sure which one it is. There's no link, so maybe somebody here knows. But these properties are the ones that are affected. I should mention, though, that there is significant erosion. Just it looks to me as though the road just west of the causeway here onto Jondron has been moved back. You may know that, but it certainly looks as though it's been moved back. And their private road here is close to being toast. So we just zoom in on that. This is looking at erosion rates. So this is a 2008 photo. And the red line is the cliff top line in 1953. So you can see that there's been surprisingly very little once you get into this more protected area. But something like 55 meters in 55 years at the lower big white arrow here, and a similar rate here. And as these are sort of pointed, as the erosion pushes back, the beach gets longer. And then on these two houses, the other one is 93 meters back from the cliff edge. That's a reasonable setback. But it has seen about 2.5 meters of retreat since 2008. And this other one, which is 10 meters from the edge, has also seen 2.5 meters of retreat since 2008. So I would call that one a much more precarious situation. One of the most spectacular erosional stories on Île Madame is at Cap La Ronde. And I'm sure you've seen the pictures of it when there was a large lighthouse on top of the hill there. The map at the left is actually Captain Bayfield's chart of Île Madame that was surveyed in 1848. The map was published in 1860, but he did the survey in 1848, and it's remarkably good considering the techniques they had available to them. And we see, fairly substantial drumlin headland and this two-armed tombolo. So tombolo is where the beaches connect to the island, and typically it is that sort of double crescent shape. Well, nowadays this is the Nova Scotia coastal hazard map app I was showing you. So the shaded relief hillshade LiDAR survey. And you can see it's just a stub now and a single bar that comes back. So a very substantial change from 1848. Eric Force, who I mentioned earlier, was interested in this. I think he lived up somewhere in Disco's Way, Portiaville, I'm not sure. But he spent a lot of time looking at the coastal erosion there. And the black lines here are his analysis of retreat of Cap La Ronde from 1938. I think it's based on a McCaskill photo, to 1975 to 1998. And then this is the 2004 Google Earth image. It's an Airbus image. So this is today. And we just have, it's just 22 meters from the back of the hill to the cliff edge today, where it was 180 meters in 1938. So that's average since 1938. Since 1938, it's 158 meters or 1.8 meters per year, and since 1998, 3 meters per year. So you can also see that increase, which may or may not be, real long-term increase. But as the drumlin gets smaller, there's less and less you need to move to get rid of more. So that's pretty much it. Some of the key messages are that adaptation measures that promote resilience are things we need to think about. And amongst these things that we can do are dune protection. We have not a lot of places with sand dunes on Île Madame, but Pondville's one. And anywhere you have dunes, they act as a natural buffer and can allow the beach to recover after storms. There are various things called living shoreline measures or green engineering, where you work with vegetation, usually with vegetation, but also living shorelines involve allowing the natural system to recover as it's wont to do. And there are other, maintaining sediment supply to beaches. So, if you build a seawall in front of one property, it actually can create erosion in the next because the sediment transport is cut off. And very often these barriers between headlands that fail are because the supply of sediment has been reduced. So finding ways to keep the sediment flowing in the system, allow it to respond more effectively to changing forcing. And then there are various legal approaches that can be taken to encourage avoidance of the hazard. And so we actually talk about coastal adaptation in terms of, one response is protection, build a wall. And if you have something like Fortress Louisbourg, you might need to build a wall and protect part of it. But that wall will need maintenance and eventually will fail. Or various kinds of adaptation, like building on stilts or building higher, or having a greater setback where you build. And ultimately, the best protection is to avoid building in a risk zone in the first place. So avoidance is cheaper than proactive. So proactive retreat is actually preferable to forced retreat, but avoidance is even better and cheaper. And that whatever we do, the coast is going to migrate because the sea level is changing. So erosion isn't necessarily bad. In fact, erosion can be good because it makes beaches. It generates the sediment that allows beaches to develop. It's only a problem if something is in the way. And then the other thing, as I said, it's ever changing. The coast is a dynamic interface. And so it's subject to long-term change no matter what we do. This is a quote I like. Along mile after mile of coastline, the land presents a changing face to the sea. Each is the seacoast, yet each is itself like no other in time or place. In every outthrust headland, in every curving beach, in every grain of sand, there is the story of the earth. And that was written by Rachel Carson, who wrote The Silent Spring. Thank you.
For educating us on a very important topic relevant to Île Madame. Do we have any questions from the audience?
I may not have the terminology correct, but I understand that Île Madame is a bit geographically distinct and significant because of the type of aggregates that we have here, if that's the right terminology. Some of the rock formations and what can be seen from the surface is been pushed up from stones that weren't there 50 years ago. And I'm just wondering if that's part of the erosion, or if it's part of the fault, or if it's just age of that stone over time, but it is causing banks to fall at a pretty rapid rate.
Are you talking about a natural bank or something that was built?
These are solid aggregate stones that have been um, visible for as long as I can remember. I'm assuming they've been here forever. So they're not men. They're not something that was put there. It's not
Okay,
cement. It is actually a geographical or geological feature that's distinct here.
Yeah. I'm not sure. I know there were that corner of the island has more metamorphic rock, and that's rock that has been transformed by heat and pressure over time in the past, and is now exposed. And there's even a little bit of granite on the peninsula there, but I'm not sure about I'm not sure about what you're talking about. So I'm gonna have to
Well,
look
if you
into
walk to
that.
the lighthouse in Cape Hogus, you'll see what I'm talking about. Because
Okay.
when I was a kid, those were solid forms that we thought would be there forever, but they're actually crumbling
Well,
now.
I mean, both chemical and physical weathering can lead to rocks crumbling, and depending on what their initial lithology is, they may be more or less susceptible to that. And there is actually some gypsum on the island, but it's not in that. It's at the other end, and in younger sediments. Um, but you have me intrigued. I'm going to
Go for a walk.
see, try to have some time to do that. Yeah.
I wonder if you could speak to the issue of the natural cycles that the Earth has gone through over millions of years to get us into freeze thaw, rising water, natural process,
Yeah.
and how man has overlaid that scenario where we are now over the last 500 years, and what you see the rate of change over those 500 years. Obviously, we started with the Industrial Revolution at a very low rate of carbon production, and et cetera, where we are now. Can you separate that from the natural process of climate change that the Earth has undergone for the last millions of years?
Yeah, I mean, the climate is always changing, and part of that is changing solar irradiation, which is a function of of changes in the orbit. So these 100,000-year ice, like sub-ice ages that I was talking about, uh, are apparently related to orbital changes that lead to less solar radiation and then more. And so that is a natural process. Other things that can affect the climate are volcanic eruptions. So at times in the past where there have been massive eruptions, like in India, there were the Deccan Plateau, or even single large volcanoes can depress the temperature. There are stories of, the year without a summer, I think 1824 or something like that. Krakatoa was a big single event. But so there have been these changes, and the models, we can run the models to show what change we would expect from natural effects. We see the solar radiation effects on the last, this is just models that might run over the last 2 centuries. We can run a model, or series of models that then converge on a history without human emissions. We can run it with volcanic events, and neither one of those or the two together tell us what we see today. And if you add the emissions and the greenhouse gases, then you end up with a track record, which is this very rapidly accelerating temperature. So there have been large swings. There have been periods in the past when the CO2 level in the atmosphere was higher. We can tell this by looking at bubbles in glacial ice. And the way that we actually know that there've been 7 or 8 or 9 of these 100,000-year cycles is from ice cores in Antarctica, which go deep enough to get into very, very old ice. And we can see we can measure the carbon, the CO2 and other atmospheric components in those. But the trajectory that we're seeing today of temperature on a global average is unlike anything that we know in the recent past. Let's just say the last 10,000 years or more. Although there may have been larger swings in the past, the rate of the change is something that's almost unprecedented. And I think there are very few in the science community today who would deny that that is a human effect. It's pretty much incontrovertible that that's a human effect.
So that is so. North America obviously is a large contributor to that process. However, we have the developing world, China and India, which has not really reached our standard of living yet. And the only way they're going to get there is through the burning of fossil fuels. So what is your counter to this going forward?
So it's a wicked problem. It's a wicked problem. Yeah. Everybody would say that, all people have a right to a decent standard of living. The only solution that I could see is that we transform energy systems rapidly. We still have the issue of how do we feed people. The birth rate is dropping as well in developing countries as well as developed because of the challenges. Yeah. Thanks for the question.
Yes, hello, good afternoon, thank you for coming. There's been, in the last 2.58 million years, there have been, 19, 20 glacial advances and a warm period of between 12 and 18,000 years in between. We are now coming towards the end of a warm period, chronologically speaking. And so do you think it's possible we could have another glacial advance? I actually have a hypothesis that explains this, but I'm not going to go into it here. I just wondered if you thought it was possible there's going to be another glacial advance in the next couple of 100,000 years.
Well, if it weren't for us, that probably would be happening. And actually, we were quite worried about, I'm thinking about 40 years ago, we were quite worried about the next, when the temperatures were going to be going down. And then it became rapidly clear that they weren't because of the emissions. But yes, naturally, that would be what would happen. And it's these orbital effects that Milankovitch cycles that is far enough in the future that we have a problem to solve in the meantime. Yeah.
So it is possible.
Oh, I mean, it's to be expected. Whether we'll still be around is another question.
The question I have is much more in our timeline, like this generation. We don't have a Coastal Protection Act here yet, backed by the science you presented. So to influence community development plans, is home insurance policies going to respond faster to science, do you think? For example, rebuilding after storms, insurance today supports restoring the same footprint that was just, from the destroyed home. So, but maybe we should be setting the restored home further back on the property. But like, what about this? Who's responding to the science?
Thanks. I mean, the insurance companies are very concerned. And they're probably ahead of the curve. They're certainly ahead of government on this. There is, in fact, no insurance for coastal flooding. But I know that in many cases, people are being denied insurance if they're considered to be, in a spot that's too risky. So yeah, and insurance is going to play a role, I think. Unfortunately, I mean, what we really need is a more coordinated discussion of how to respond. So it's one thing to have the insurance companies, making decisions, another to have municipalities making decisions, and that's what the failure to implement the Coastal Protection Act has done. It's thrown the challenge back on the municipalities, which is asking a lot of the municipalities. And it means that we then don't have a homogeneous approach across the province. Depends on who's on council. It depends on the resources that the municipality has, so it's unfortunate. I mean, I can say this as a retired federal public servant. I just think it is unfortunate that we had the beginnings of a coastal policy, because really the Coastal Protection Act didn't do it all. But it is a beginning point where we would have a standard approach across the province and a basis on which to discuss further action that's needed. And the key, I mean, ultimately the key is to protect people's investment and protect people's lives. And when we saw Port aux Basques in hurricane, post-tropical Fiona, we saw how serious the implications can be. It's very difficult to envisage your place you live as being a place of destruction. But it can happen, and there are ways that we can reduce the likelihood of that. And in the case of the coastal zone, although we don't have precise measurement or predictions of where the water will come, we could give a pretty good indication of where you may be at risk or where you'd be safe. Employing those in zoning and planning and development is desirable. It's always cheaper to avoid the risk than to deal with the effects of an extreme event.
Thank you. Do we have any other questions in the audience?
Thank
All
you. I hope I haven't depressed you.